It all started with Diebold and Yilmaz Connectedness Index. As always, that's also not new because it's based on previous work and well-known relationships in econometrics, or if you like, in statistics or physics. So it's all about impulse response, and especially in a bidirectional sense. If you take a typical regression, it's unidirectional unless you want to turn the variables. Even if you turn it at any point that you make a relationship, it's unidirectional. But a typical impulse response is bidirectional. And if it's in a single variable, that's easy to do. But if you have more variables, then they become vectors and matrices, and you complicate them. Like you have the multiple relationships. They are also under the bigger umbrella of connectedness, interrelationship, interdependence. And if there are different aspects of that, you can deduce your contagion, your safe haven, the hedges, or you can even try to construct portfolios from them. Maybe we can look at that later. You can even construct connectedness portfolios. What you are usually familiar with is the mark of this portfolio approach, but you can also do connectedness portfolios from this connectedness approach. So we'll start with some basic illustration, I'll try and go through the equations with you. So we can start with this one. Now, first of all, this is in a time series framework or time series world. So in a typical time series, if we believe that we can use an AR model, an autoregressive model for that one, which is the one we are looking at here. If we are restricted to this equation, for example, the last term, which is the error term, can be our source of what we call innovations or shocks. If you want to capture the structural shocks in the system, we can pick that from the error term. In fact, a number of structural models extract the structural shocks from the error term. So if you have specified your model correctly, you can extract your shocks from the error term. Now, if we go back to our time series methods, we have the AR, then we have the MA, then we combine the AR and the MA to get AMA, then we can take a difference, it becomes ARIMA, all of that. What you realize is that the MA is a polynomial of the error term. So the MA will usually have the form of the error term in powers of 1, 2, 3 as the new equation, if you believe the AR was not able to model the data correctly. Okay. This is important because to get our impulse and responses, we are going to adopt the moving average approach. So if it is structural, we'll just use the error term and construct a moving average. But if it's not just structural and it's a number of variables in a system, we'll still use the moving average approach and find the innovations or the shocks. So if you take this here, it's a typical stationary series. If you do a moving average, you want to find the units of you want to find the roots of the equation where they should lie within the unit circle to be stationary. You can represent it as a moving average. So if you look at this, I indicated that it's polynomials of the error term. So you can see UT here of power 0, that makes 1, then power 1, all the way to however many that you have. So that is if it's stationary, it may not be stationary. As we go along, realize that we premise the technique on stationarity, which if you are doing our descriptive stats, you may have to show. Okay. Now, So this is if you have a single series. But you may not have a single series. In fact, you will usually not have a single series. You have a number of variables, vectors and matrices. So then you can represent it in a matrix form. So this B here will be a vector, and this will also be a vector. So we have a vector of variables and their, if you like, their coefficients as well. So we change this equation in terms of U to in terms of the vector B or the matrix B. Okay, and that's why you have it here. Now, again, if you look at it, it looks like a regression equation. Of course, it's autoregressive, so it's a regression. And each of the coefficients will be the marginal contributions of the terms. So ET minus 1 will have beta of phi, and phi squared VT, ET minus 1, its marginal contribution is phi squared BT. And that's very important because even if you have a regression, you have this delta, partial derivative of y giving a particular x. So they are marginal contributions. Again, if you are still in the system, I mean, you are in the error term as without bringing external variables. Okay. So here, what we are looking at is the shocks from the error term only. But what if the shocks can come from any of the variables in the system? So the shock can come from maybe GDP, from inflation, from money supply, all of those things. So that's what we'll look at them to be. Now, so this is what I mentioned earlier. So this will be the response of ET to the shock in the data, okay, for B at time t. If you have time t plus 1, so realize that the coefficient of t is B, coefficient of t minus 1 or t2 corresponds to phi beta or B. Okay. So we can generalize it to phi of j, so any other will work. So we can leave it here and move to the other side, the other part that I want to show you. Okay. Now, so as we are moving to that side, what we need to bear in mind is we are looking for a shock in a system and the response that is given in the system. In a typical structural form, it will come from just the error term. But if it's not in a structural situation, it can come from any of the variables. And that's very important to know because when we look at the matrix, even where we are going to pick the shocks and the responses from will be crucial to knowing the shocks. So in a typical matrix, what you want to know is if you have a shock from one variable, what is the response from all the other variables together, each of the variables, and whether the responses are even more than the shocks and vice versa. And so that's what we want to look at. So if you go here, you may have seen this paper. So I'm looking at the methodology from that paper to show you. So in a typical matrix form, it's going to be like this. So this is just a matrix representation over time t, and we are using a VAR. So if it's a single series, then we are doing autoregression. But if it's a matrix, then it becomes vector autoregression. So this is typically a vector, okay, with these coefficients and a lag of 1. So what we want to do is to decompose this matrix or this VAR model with what we call the generalized forecast error variance decomposition. So what this one does is going to find the variance or the forecast error of each of the variables as against the rest of the variables. So shock in one system over the other. Now, you see this is generalized. This means that the original one was the forecast error variance decomposition. We are employing the generalized because this is more flexible, can handle complex situations, especially non-linearity and time varying, which is very important. So that's why I'm using the generalized one. Okay. And this is what the Diebold and Yilmaz model started with. Okay. So for a matrix, we have this same characteristic equation that we saw in the AR model. Okay. And we can get that from the moving average representation, so of any order. Now, when we get to TVP-VAR, it is the same thing, but there's something we call the word representation that is used to do the MA representation. So it's basically the same thing, just a specific variation. And I indicated when they lie outside the unit circle or not for stationary. So that is this part. So what we are looking at is the role of the K variable as compared to the variance of the forecast error in any element of the matrix J. And that is written as this. So what you are looking at is a form of marginal contribution of one as against the other. Now, what I'm going to show you briefly is important. So if you look at this equation, there is almost no difference between the one at the top and the one below. Almost no difference. The only difference here is the matrix that is indicated here. So from H to H0 to H0, we have a square here, which is sort of a modulus. Here, it won't make a lot of sense because we are not in complex numbers yet. Now, what is going to be evident is that if you use this form of forecast error, you are not going to aggregate the components to 1. You are not going to aggregate the components to 1, which is a problem because if it's in a system, they should sum up. So what we do is that we standardize it. By the standardization, we now reduce the equation 3 to equation 4 here. Now, equation 4 looks more interesting because what we see is a component of J as against the whole component. So you see part over whole here. And that's what is important to note. Because now we are going to look at the shocks from one variable at time I as against the response from the other variables in the system. So part over whole, that's what we should note. And this is what I've highlighted. The proportion of variation in predictions, it doesn't have to be predictions anyway, provided by errors other than own errors, which is ratio of the off-diagonal component sum to the whole matrix. In the TVP-VAR literature, when we will look at it, they will call it the corrected connectedness because there are instances that you do not go through the off diagonals. You just look at the diagonals and you realize the diagonals will be the self relationship. If you look at if in a typical variance covariance matrix, you know what is in the diagonal and what is off the diagonal. So that doesn't depict the relationship across the variables. So we look at the off diagonals. That will be the sum of everything else against the diagonals. Okay. Then so for the off diagonals, this is what is important, that J is not equal to K. So if it is off diagonal, then J is going to be equal to K, or you can have JG or KK. So that's what we need to do. So off diagonals against all the system. We can multiply that for interpretation purposes. So the diagonal sum is the denominator, and no, the whole sum is the denominator and the up diagonal is numerator. That goes back to the original part over whole that we are looking at. So this is basically how the generalized variance, forecast error variance decomposition works. But before I come to continue from here, I want us to look at the TVP-VAR framework and juxtapose it. Okay. So the Diebold Yilmaz method, the Barunik Krehlik, the one that we just saw, and the TVP-VAR framework are very similar. The Diebold Yilmaz one does not consider causality within a spectrum, let's say within a frequency band. And originally it was not time varying. So it was just a VAR. You couldn't do it in frequency domain. It was just a static framework. But the Barunik and Krehlik method induces causality, which was within a spectrum, minus pi to pi. And it is also time varying, even has a rolling window portion to it. Then the TVP-VAR, there's another step to it. And that step is the forgetting factors. Forgetting factors. What are the forgetting factors? So if you are doing forecasting or modeling in a typical time series framework, what you want to do is to apportion weight to different portions of the data. So you would want to give more weight, for example, to more current data than old data. So T minus 1 should typically have more weight than T minus 5 or T minus 10. And that's what the TVP does. It apportions higher weight to current data as compared to old data. So if you look at all the components of the Diebold and Yilmaz, you take Barunik and Krehlik, and you add this to it, that gives you TVP-VAR. So those two parameters that we call forgetting parameters, one is taken from exponential weighted mean and another is taken from just a VAR. So when we put those two together, then we change the dynamics. That means our forecast analysis is not giving equal weight to all the data points over time. It's giving specific weights to different portions of the data in terms of time. So that's the TVP part, time varying parameter. And we shouldn't confuse that with the whole method, which is already time varying anyway, because it's a time series, it's a VAR, you can plot it over a period or even over frequency domains. But the time varying parametric part is the forgetting factors. Those are the only differences that comes in. So if we take a typical vector, so this is not any different from the other one. So we take vector of lag 1. When you go into the code, we will see where the lag 1 comes in. So this is a vector, and we are going to form a moving average from it. So that will be TVP-VAR, TVP vector moving average. And that is also going to be based on the generalized forecast error variance decomposition as the impulse response function. So we can look at it in this way. So in the moving average format, it changes to, we bring in the error term over a long span. You remember the MA from Barunik Krehlik was to infinity. So this is the same representation here. And from this, we can get the impulse response function, which represents all factors G to a shock in the variable I at time t. And again, earlier we said we're going to look at the corrected one, which was off diagonal. So here, what is happening is that we use the forecast. The impulse response function is basically a difference between shocks to the variables and the part that was not shocked. So because it's different parts of the data, so some parts will take shocks, others will not be shocked. And we can take a conditional mean of this form. Okay. Now, this conditional mean, so if you look at here, if you look at this part, the condition is the shock, and if you can look at it as over the forecast length of J. Usually they write H, but we can use any one of them. So J. Okay. Now, what is happening is that you look here, you see JJ. So the part, the shocks from ET or EJ over JJ, this is the diagonal. So that's why I've highlighted them. So you see the same variable, so it's the diagonal. And this is just another representation of that. And this is not the best because obviously that is like looking at variance rather than covariance. And covariance is what's going to give you the relationship that you're looking for. So based on the variance decomposition, we can look at the part as against the whole. So from J equal to 1 all the way to N, that will be for the whole data set. And you realize that this is also IJ instead of JJ. And that is clear if you come here. And that's the one we call corrected. So from the BK framework, we saw the off diagonal to be J not equal to K, I think. So here we have I not equal to J, which is the same thing. And we have the impulse response function here. So this portion is this whole equation that we have inserted here. And that is the off diagonal. So what we are looking at is the shocks in the system at time t to variable j or variable I over all the other entries in the matrix. That still comes back to the part over whole. And because this is based on forecast error variance decomposition, that is a typical impulse response. So having said that, we can now pick out the shocks that are being received and the shocks that are being received. So you have one variable that is receiving shocks from all other variables, which means the system, but it is also transmitting to all the other variables. Then you can also pick out the pairwise relationship. So if GDP is transmitting to inflation, inflation may also be transmitting to GDP. So you can find their pairwise relationship. And for that, you can also pick out which one is bigger and which one is smaller. That will give you a net. So if you take a subtraction, you have a net. And if your net is positive, it means one is the transmitter is more dominant than the recipient. If you have negative, then the reverse is. So we can pick all those ones from the forecast error variance decomposition. As far as we're able to get the structure for equation 19 here, we can get the 2 from and all the other parts. So those are the ones that are following here. So if you look at this, it says it is I to J, and that is 2. So then you can come here, you see J to I, just the reverse. And you can find the net, which will be the difference. That's the equation. And that can also lead you to the net pairwise connectedness. So this net here is not just bidirectional. It can be net between one variable and all the rest. Because if you have a system, you can have a single variable in a system of, say, 10 variables that can even dominate all the other variables. So you may also want to find them in specific pairs. So if you look at this, you have J to I or IJ and then JI. That's why I've highlighted them in different colors for references. So you realize that here, from here, it says this can be done in frequency domain analysis. So with this, I'll go back to here, and so that we can talk about the frequency domain. So generally, frequency domain or even time frequency domain analysis is referred to as spectral analysis. So if you're able to find a forecast error variance decomposition, which will indicate our impulse and response function, in what we have done so far, that is in the static framework. But we can also do this in the spectral form, in a frequency domain framework. Now, when it comes to frequency domain, you are in form of a space. If you remember what we did in wavelet, we had, or we said that if it's time frequency domain, then we will look at the Heisenberg's uncertainty approximation. So an object in space and motion, you cannot really determine its position, so you approximate. Okay. But here we are just in frequency domain. Later we'll look at time and frequency domain. So we need to be able to put this in space. And if you are putting it in space, usually we'll have to come across the angles that we have to deal with. Because what is happening is that eventually we need to know a leading and a lag. We need to know modulus, which is the magnitude, which is we also call the amplitude, and you have to know which variable is leading or lagging. And in that case, we need to venture into complex numbers. But it is only when we are in complex numbers that we can transform our angles into modulus. So that gives us the IW, where W is the frequency and I will indicate our complex number. And most of these frameworks are based on the Fourier transform. Even wavelets are based on the Fourier transform. If you take the Karma filter that the TVP-VAR is based on, there are different variants of the Fourier transform. So we take the Fourier transform to represent this frequency W, let's say omega, in MA form. So this is the MA representation. So if you are in complex numbers, we always have the positive and the negative to give us the angle, which we call the conjugate. So in that framework, we can find the spectrum between minus pi and pi. That will basically give us the whole circle. So one part of the circle and another part where we can construct our angles. And this framework we call the causation spectrum. And again, it means that the shocks in the system are happening within those particular framework, those particular bands, which we'll call frequency band shortly. We'll see that very soon. So in a frequency band, this is the connections, the shocks, and the responses that are happening. Okay. And that's what we have represented here. Okay. So again, if you look at this, we have JJ here, but we have JK. So this is not the best that we have to do, as we indicated earlier. So we can transform them. But before we do that, this is something that we should take note of. We realize that we have a square of a complex number. In complex framework, when you take a square of a complex number, it becomes a real valued number, which is very important. Then we can, because we are not going to interpret our results in complex numbers, we need to interpret them in real numbers. So there should be a point after being able to put them in spectral format to transform it in real valued numbers for interpretation. And that's why the square of the complex number is important. So we now weight the function as the share of the variance of the J variable as compared to the variable in the system. So if you look at this part, this is the whole of the circle, if you like, because from minus pi to pi, and this will be just a part of the circle, and that brings us back to shocks in one variable as compared to the responses in the other variables. So normally you may not find, if you read some of the papers, you may not find they may not present the frequency domain aspects of the methodology. So you can pick it from this and take it to that side so that you have a complete method. But for some reason, maybe there isn't a lot of space. People can just overlook it. Okay. So in the spectral form, what we do is look at the representations. So in frequency band, that's important because we look at it in bands instead of at specific frequencies. So maybe between, if it's daily data, maybe between 1 and 5 days, then from 5 days to 10 days, if it's monthly, like that. So we can change it and represent it in bands. Earlier it was minus pi to, was pi to minus pi, but it's now in frequency bands A and B, where A is less than B, because move from the first frequency to the other frequency. So this is just another representation. And if you look at it, it is now the connectedness value that we have from 8 that is being represented here. It is now only in the frequency band. Nothing has really changed. Okay. So I've indicated that one here. So this is just the same thing that I was going to tell you there. So according to Barunik and Krehlik, this is how you set the frequency bands. The first one is usually pi plus this specific number, and usually have multiples of 2 from there. So pi over 4, then maybe pi over 16. But you have the freedom to choose any of the frequencies or the bands that you want to, based on your data. For example, if you have a yearly data, there's no reason you are going to choose pi over 32. No, nobody's interested in 32 years. And your data may not be that large for proper analysis. So the choice of frequency band is important, but should be in the context of your study. If you go back here, this is the same thing that we're trying to do here. So if you look at this data, this work, for example, there wasn't a lot of data. It was like, I think it's a quarterly data. So I chose only 3 frequency bands. So you realize it'll be from this, come on, here to here, here to here, then there. So that will be 3 frequency bands, not 3 numbers. So if it's quarterly data, we have 1 to 2 quarters, and 2 to 4 quarters, and 4 to infinity. So however many that they are. Okay. So this is, let's say, the condensed form of how the description of the methodology is. There's one thing that I have to show you here. I think there's a forecast horizon, because this is, remember, it is forecast error variance decomposition. So there's always a forecast horizon that has to be chosen, and you will see it when we start looking at the code. So far, for now, this is so this is basically the same thing that I've showed to you. I've highlighted them. You can make reference to them. Okay. So what I want, so I'll look at the package as usual. We look at some portion of the package that we are going to use. Then we can look at the code. So the 2 main packages that have been developed. So one is like an umbrella. We have the frequency connectedness package. So this includes the Diebold and Yilmaz of 2009 and 2012, as well as the Barunik Krehlik. Then the connectedness approach. There's a connectedness approach, which is an umbrella for all the various connectedness indices: TVP-VAR, Barunik Krehlik, Diebold and Yilmaz, joint, R squared, extended, all those ones. So we will start this evening with the frequency connectedness. So this one here, I'll show you a few things that we need to see. If you go into the code, remember I always put the notes on the code. So if you are doing some exploration, you can just look for your forecast error variance decomposition, just that. But we are usually not interested, because when we do our main analysis, those are inbuilt. So we are going to use a number of functions. So if you see the dy09, that's going to compute the Diebold and Yilmaz 2009. Then there's the dy12, that will be 2012. Then who venture into the Barunik Krehlik, that's also a different representation. And once we're able to do that, we can start extracting the to and from and the net, and the total, and the pairwise, all of those things. In the TVP-VAR, is basically the same thing. Once you're able to extract the composition, we can get the to, from, and all of those ones.